Let's get right into it. Today, we are decoding a really fascinating lineup of highly specialized mechanical seals. We've got this one brilliantly laid out image that we're going to use to demystify 12 distinct components. And I'm absolutely thrilled to walk you through this explainer because it perfectly shows how something that seems so incredibly basic actually hides a massive amount of engineering. We aren't just looking at random rings of material today, folks. We're looking at highly engineered solutions built to handle extreme pressure, brutal thermal expansion, and highly corrosive chemicals.
Just take a look at this spread. Arranged perfectly right here on this wooden surface are 12 completely unique mechanical gaskets. Now, before we even worry about the names or what each one does, just consider the sheer variety of engineering on display. These simple rings are literally the unsung heroes keeping the mechanical world running. But why do we even need them? Well, think about it like this. No matter how perfectly a metal pipe flange is machined, at a microscopic level, its surface is completely full of jagged peaks and valleys. If you just bolt two metal pipes together without a gasket, high-pressure gases and fluids are going to find those microscopic imperfections and leak right out. So, these 12 distinct materials exist specifically to be forced into those tiny imperfections under immense torque, ensuring that dangerous or pressurized substances stay exactly where they belong.
Okay, let's dive into this taxonomy. To really make sense of what we're looking at, we're going to group these 12 items into logical families. We'll kick off with a quick look at the world of gaskets as a whole, then we'll break them down by their dominant traits: heavy-duty metals, flexible synthetics and rubbers, highly textured fibers and graphite, and finally, a look at some completely unique form factors, before we wrap the whole thing up.
So, let's start our journey with Section 1, the world of gaskets, a taxonomy of seals.
If we look really closely at the shared DNA of everything laid out here, we can actually build a working definition. Simply put, based on what we're seeing, a gasket is a flat, typically circular mechanical seal designed to sit right between two surfaces. But mechanically speaking, a gasket works by yielding. It plastically deforms under compressive force. It literally crushes itself to fill the macroscopic and microscopic irregularities of those mating surfaces we talked about. And as this lineup makes incredibly clear, the word gasket doesn't just mean one standard thing. There is a massive, almost overwhelming variety in the materials and textures used here, and that's entirely dictated by the specific extreme environments the gasket has to survive in.
That brings us right to Section 2, heavy-duty metal options. These are the seals built for serious pressure.
Now, what's really interesting about this group is how we can immediately single out items 2, 5, 6, and 8 purely based on their rugged, metallic appearances. Number 2 is the spiral wound gasket. You can spot it by that green outer ring protecting a tightly woven metal inner core. Number 5, the metal jacketed gasket, has this really smooth, layered steel look. Then there's number 6, the camera profile gasket. It stands out with a bold black inner ring and this very distinct metallic loop sticking out from the edge. And that rugged look isn't just for show, by the way. The camera profile actually uses a solid corrugated metal core designed for extreme blowout resistance in high-pressure piping. And finally, number 8, the copper crush gasket, which is just a solid, bright ring of copper. To really appreciate the level of engineering we're talking about, let's contrast two of these heavy hitters in depth. Check out the spiral wound gasket number 2. The combination of that solid green outer ring and the woven, almost spring-like metallic intersection is absolutely brilliant. This specific design is all about surviving thermal cycling. Imagine a pipe system that has freezing cold liquid running through it 1 hour and then boiling hot steam the next. Those metal pipes are constantly expanding and contracting. Well, the spiral wound gasket acts like a literal spring, expanding and compressing right alongside the pipes, maintaining a perfect seal despite all those fluctuating forces. On the flip side, the copper crush gasket, number 8, operates on a totally different principle. Copper is a relatively soft metal, right? It work hardens or can be annealed. So when you apply immense torque to this solid piece of copper, it plastically deforms. It literally crushes down to create a permanent, impenetrable seal. That makes it absolutely perfect for high-temperature exhaust environments, like in engines or aerospace applications, where a standard synthetic gasket would instantly melt into a puddle.
Now, you might be wondering, if metal is so strong and reliable, why wouldn't we just use metal for absolutely everything? Well, that brings us to Section 3, synthetics and rubber seals. These are the flexible and smooth members of our dozen. When we look at items 3, 4, and 11, we're seeing a complete departure from those rigid metals. We've got the classic rubber gasket at number 3, featuring a perfectly smooth finish that just screams ultimate flexibility.
But the real engineering marvels are sitting right next to it. Number 4, that pristine white PTFE gasket, is essentially pure Teflon. It's used specifically because it is almost entirely chemically inert. You're going to use PTFE when you have highly corrosive acids or aggressive chemicals flowing through your pipes that would instantly eat through rubber or severely corrode solid metal. Finally, number 11 is the silicone gasket. With its translucent, frosted appearance, silicone is highly prized for being biologically inert and completely stable at extreme temperatures. That makes it the absolute go-to standard for food-grade processing plants, pharmaceutical labs, and high-purity medical environments. If we look back at the main spread, these 3 really stand out, not just for their sleek finishes, but for what they tell us about the systems they belong to. See, in mechanical engineering, there's this crucial concept called bolt load. Basically, this is the amount of physical force required to compress a gasket enough to make a perfectly tight seal. Those heavy metal gaskets we just looked at, they require massive bolt loads. We're talking literally tons of force. But what if your piping system is made of fragile PVC plastic? Or what if it's glass-lined piping in a specialized chemical plant? If you tried to torque down a rigid metal gasket on a fragile glass flange, it would shatter instantly. No way around it. So these smooth, pliable synthetic surfaces require a much lower compressive load to achieve a perfect seal. They protect delicate, non-metallic piping infrastructure while still keeping dangerous fluids completely locked down.
Moving right along to Section 4. Let's examine fibers and graphite materials, the highly textured composite solutions of the group.
And this brilliantly illustrates just how varied gasket materials have to be to handle highly specific industrial threats. Just look at the engineering we're dealing with here. Number 1 is compressed fiber, which has this incredibly densely packed dark gray texture. Then there's number 7, which is historically pretty significant, the non-asbestos gasket. For decades, the industry relied really heavily on asbestos for heat resistance. But for obvious health and safety reasons, they had to pivot to non-asbestos blends made out of Kevlar and aramid fibers. Actually, that's exactly why manufacturers now proudly print their logos directly on the material, so engineers can quickly verify it's safe to handle. Number 9 is a standard fiber gasket, practically leaping off the table with a bright, vibrant color and a distinct porous look. And then there's number 12, expanded graphite. It has a highly textured, almost scaly or snake skin-like pattern. That totally unique structure allows it to withstand absolutely insane, extreme heat in refineries and power plants without oxidizing or losing its springiness. Let's actually compare 2 of these fiber-based options side by side to really dig into the chemistry. You've got the compressed fiber gasket, number 1, in that dark, dense gray. Now that implies something really tough, but mechanically, the dark color often comes from the specific binders used to hold the fibers together. A dense, dark fiber gasket like this is typically heavily bound with nitrile rubber, which is specifically engineered to provide extreme resistance to petroleum, fuels, and heavy oils. Now compare that to the standard fiber gasket, number 9. Its bright teal color and slightly softer appearance indicate a completely different binder chemistry altogether. This type of gasket is usually tailored for much less aggressive environments, think municipal water lines, mild steam, or inert gases. So even within a single broad category like fiber, the precise chemical makeup and the resulting real-world applications are night and day. For Section 5, we need to talk about unique form factors. Pretty much everything we've looked at so far has been some variation of a simple ring, but there's one glaring exception here.
Let's move over and see how this builds a totally different kind of mechanical connection. If you look down at the bottom left corner, gasket number 10 completely breaks the mold.
This is known as a full-face gasket. While the other 11 items are essentially just open rings, number 10 features a much wider body with 6 distinct, mathematically spaced pre-cut bolt holes. To understand why it looks like this, we have to introduce 2 fundamental engineering concepts, the raised face flange and the flat face flange. The other 11 gaskets are designed for raised face flanges, where the sealing surface is slightly elevated and the gasket sits completely inside the bolt circle. But number 10 is designed for a flat face flange. That's an application commonly used in brittle cast iron or older plastic systems. Because the flange material itself is fragile, the bolting force has to be distributed perfectly evenly across the entire surface area to prevent snapping the pipe flange right in half. The bolts actually physically pass through the gasket itself, locking it into a perfect wide stance seal. It's a fantastic mechanical strategy designed strictly to protect brittle infrastructure from its own clamping force.
And that brings us to Section 6, wrapping up the dozen. We've seen 12 totally different solutions, all ultimately serving one primary purpose.
12.
That is the number of entirely distinct, highly specialized engineering variations presented to us for what, to the untrained eye, seems like a universally simple task, sealing a tiny gap between two pieces of metal. But, as we've discovered today, that simple task is actually a high-stakes battleground of physics. These components are constantly fighting against extreme thermal expansion, resisting highly corrosive acids, and holding back immense crushing pressures, all while sometimes needing to actively protect the fragile flanges they are bolted between. Looking back at this complete lineup, you can now truly appreciate the engineering journey we've just taken. We didn't just look at random shapes and colors. We've seen metals engineered with spring-like cores for extreme thermal cycling. We've explored pure Teflon built to literally shrug off highly corrosive acids and high-purity silicone made for pharmaceutical labs. We observed the aramid fibers that safely replaced asbestos and expanded graphite designed to survive absolutely insane heat. And we recognized how full-face rubber gaskets actually physically protect brittle cast-iron pipes from snapping under bolt load. All of this incredible, specific engineering, perfectly organized into one collection.
So, the crucial point is this. We've spent this entire explainer looking at just one single type of mechanical component. With 12 highly specialized designs existing just to create a simple seal, what does this tell us about the hidden, mind-boggling complexities of the everyday machines, cars, and piping systems all around us? Next time you see an industrial machine, or honestly, even just the plumbing in your basement, remember this discussion. Remember just how much specific, intentional engineering is hiding right beneath the surface, quietly keeping our modern world intact. Thanks so much for joining me on this deep dive.